Hello and welcome to our webinar. Our topic today is Lateral Load Path Basics, Tracing the Wind Load through a Wood Frame Structure. My name is Karen Beebe and I'm the Western Region Manager for APA, the Engineered Wood Association's Field Services Division, and I'll be the moderator for today. The seminar today is approved for continuing education units through AIA and ICC. Following our program, you'll receive a link to download your customized certificate of completion. Your feedback is super important to us. If you haven't noticed, we have a QR code here shown on the slide. Pull out your smartphone, open up the camera app, point it at the QR code, and that will launch to our customized survey for today's event. This will help us improve our future webinars. Cathy is our speaker for today. As a member of APA, I'd like to take a moment and introduce you to our association and to our speaker, and then we'll go ahead and get started. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products used in construction today. In addition to quality verification and product testing, APA conducts research to improve the products as well as the applications that you may utilize them in. We provide education for users and specifiers on the proper use as well. Cathy is our engineered wood specialist who is located for us in Texas. And she works with the design community and the builders and code officials in Texas to assist on the proper use of engineered wood products. Prior to joining APA, Cathy spent 6 years as a structural engineer designing buildings of all types, from steel to concrete, masonry, and most importantly, wood. And she also worked for 18 years in working for general contractors in the non-residential construction industry. She had a focus on quality assurance there, had different roles from field inspection to managing a quality program. Cathy is a licensed professional engineer in the state of Colorado. She's a graduate from the University of Wisconsin in Madison with a Bachelor's of Science in Civil Engineering. She also has an MBA from Colorado State University. And with that, I'd like to welcome you all to our session. Today's topic is Lateral Load Basics, Tracing a Wind Load through a Wood Frame Structure. And I'll now turn our microphone over to our speaker, Cathy Scarince.
Thank you, Karen. I would first like to mention that APA has developed design and construction recommendations that are based off of damage observed by APA field staff and others following storms. When observing storm damage, we look for patterns in the failures to determine the most common first failure points. Today, as we trace the path that a wind load takes as it moves through a structure, we're going to look at images from some of these past storms and relate them back to their initial load path failure. The publications shown here and hundreds more are available for free on our website at apawood.org. These are our learning objectives for today. They were listed on the web page when you registered for this webinar, so I am not going to read through them again for you. Today, I'm going to explain exactly how a wind load moves through a house. This is often very misunderstood, and because of that, the importance of certain details and connections are misunderstood as well. Once you understand what happens within a wood frame structure when the wind blows, the common details you see every day will start to make more sense. We will start with the basics. I will explain what a load path is, and we will talk about how braced walls work. Next, we will look at what can happen to a house when there is a lateral load path failure. And finally, we will trace the lateral load path itself. I will first go through the load path at a high level to give you a general understanding of how the load moves through a wood frame structure. Then I will go back through it at a detailed level and explain exactly how the load moves through each member and connection. As I do this, I will also point out common framing errors observed at these locations, and will also discuss code requirements where applicable. It will be helpful to understand some basic concepts before we discuss our main topic. We'll start by defining load paths and understanding how braced walls work. When an engineer designs a structure, they look at all the loads that are applied to that structure and then create what we call a load path for each of those loads. There are two kinds of load paths, vertical and lateral. Both need to be complete for a structure to be properly designed. They are both required in the IBC and IRC. The purpose of the load path is to take the load from where it is applied to the structure and get it down to the foundation and into the ground. Every load that is applied to the structure must have a load path that takes it down to the foundation so that it can exit the house. Everyone understands the vertical load path. It's just gravity, and we're all familiar with gravity. The vertical load path takes loads like snow loads on the roof, the weight of the furniture and people in the house, and the weight of the house itself, also known as dead load, from where they are applied to the structure down to the foundation. The lateral load category consists of wind loads and seismic loads. The lateral load path is not as intuitive. One of the things people find surprising about lateral loads is that in some cases, these loads actually move upward through the house before they move back down. But just like vertical loads, all lateral loads must have a path that ultimately takes them down to the foundation and out of the house. In this webinar, we will be focusing on wind load. The seismic load path has a lot of similarities to the wind load path, but there are some key differences. And since wind is present everywhere and seismic is present in only limited locations, we'll save a discussion on seismic load path for another webinar. Let's take a closer look at wind load. When the wind blows on a house, the side of the house it is blowing on is called the windward side. Another thing most people don't realize about wind loads is that as soon as the wind blows on the windward side of a house, it immediately creates two additional loads on the house. A horizontal suction force occurs on the leeward side of the house, which is the opposite side of the windward side, and a vertical suction force or uplift load occurs on the roof of the house. These additional forces are approximately equal to, or in some cases, greater than the original wind load on the windward side of the house. All of these loads, including the uplift load, must be accounted for by the load path. One major part of the lateral load path is the bracing system of the house. When I use the term bracing in this presentation, I'm referring to both engineered shear walls and prescriptively designed braced wall panels. The general load path is the same for both methods of design. Bracing can take several different forms in a wood frame structure. IRC section R 602.10 on wall bracing has 16 different bracing methods. These methods include panel type products, let-in bracing, and portal frames. For simplicity, this webinar will assume a panel type bracing, such as wood structural panel wall sheathing, is used. Let's take a quick look at how bracing systems work. A stud wall by itself, in other words, without any bracing, such as wood structural panel, has very little stiffness. When a load is applied to a wall that doesn't have any bracing, the nailed joints between the studs and top and bottom plates act like hinges and are actually called hinged connections because they bend easily. The wall can be pushed over by a load applied to one end with minimal effort. When a panel type product is attached to wall framing, the panel's ability to resist forces is imparted to the wall. This is why panels are commonly used as bracing. They resist being forced out of shape. The ability of a panel to resist loads is dependent on the physical properties of the panel, primarily its thickness. The thicker, more rigid each one is, and the more panels that are added to a wall line, the more resistance or strength the wall gains. The fasteners used to attach the panel to the framing will also affect the lateral resistance of the wall. Tighter fastener spacing and larger fastener size will increase the strength of the wall. Bracing makes the hinged connections rigid connections and transfers the lateral load through the panel to the bottom of the wall. In other words, the panel becomes part of the lateral load path. Other types of bracing, such as let-in bracing or portal frames, work by a similar concept, by creating more rigid connections and creating a path for the lateral load to reach the bottom of the wall. There are a few different types of whole house failures that can happen to a house with an incomplete or weak lateral load path. Of course, there are also localized failures that can occur, and we will discuss those when we take a detailed look at the lateral load path later on in the presentation. First, let's look at the three most common types of whole house lateral load path failures that we observe after high wind events. The first type of whole house failure that can happen is what is called racking. Racking occurs when the wall bracing in a house is not strong enough to carry a lateral load from an upper part of the house down to the foundation. The bracing fails and the shape of the house changes from a rectangular shape into a parallelogram. The damage shown in this picture is a good example of racking. The wall sheathing on the front of the home was attached with only tack nailing. You can see the parallelogram shape of the house. This house experienced racking due to a straight line wind. The bracing system of the house was unable to transfer the wind load down to the foundation. When the bracing failed, the wind was able to push the house out of square. Another type of failure that can occur is called base shear. Base shear occurs when a house is not sufficiently anchored to the foundation. As the lateral load attempts to move from the framing members into the foundation, the connection between the house and the foundation fails, and the house slides off the foundation. This house remained relatively intact as it slid 45 feet off its foundation during a tornado. A third type of failure is called overturning. Overturning results when the house is not sufficiently anchored to the foundation with hold-down devices. Hold-down devices are used to resist overturning. These are two examples of wood frame structures that have overturned. Note they are both still fairly intact, meaning the bracing system successfully transferred the lateral load down to the base of the structure. However, the lateral load created an overturning force that exceeded the strength of the anchorage of the house to the foundation, and the structures tipped over. Let's take a closer look at how overturning happens. If we have a wall with only one panel as wall bracing, when a load is applied at the top of the wall, as shown, the wall will want to tip over, with the bottom left side of the wall tilting up away from the ground. This is similar to what happens when you try to push a tall, skinny filing cabinet. It wants to tip over. This is what can lead to overturning of a structure and is why hold-down straps are required in some situations. They prevent the wall from tipping over and are literally holding the house down. By adding more panels to that same wall, you reduce the overturning load and reduce or eliminate the chance of overturning the structure. It would be like taking that tall, skinny filing cabinet and stretching it out. Now, when you push on it, it's less likely to overturn. This is why engineered houses with limited locations for bracing typically need hold down, and prescriptively braced houses typically don't, except for some methods that use narrower braced wall panels. Houses with limited bracing locations take the tall, skinny filing cabinet approach by usually using stronger bracing methods in order to minimize the linear footage of bracing, thus requiring hold downs. On the other hand, the prescriptive bracing section of the IRC, section R 602.10, makes sure to require enough linear footage of braced wall panel to prevent overturning, thus eliminating the need for hold downs in most of the methods allowed by the code. Hold downs must be installed properly to be effective. One error that is commonly observed is improperly locating the hold downs. When the wind blows from the left, the lower left corner of the panel will experience the largest overturning load. So this is where the hold down needs to be located. When the wind blows from the right, the opposite is true. In this photo, both hold downs are installed on the right side of the panel. When the wind blows from the right, the panel will probably be okay. But when the wind blows from the left, there's nothing to provide a load path for the overturning load that will occur on the lower left corner. Without a complete load path, the panel is likely to separate from the foundation. Hold downs should be installed on the furthest edges of the panel in order to be the most effective. Before we get into the details of how a wind load moves through a house, we're going to take a 30,000-foot view of what the lateral load path looks like for a wind load. Then we'll go back and retrace the lateral load path again, and I will explain in detail how it moves through each of the framing members and connections. Let's start with the big picture. When the wind blows against the house, it blows against the cladding of the house. There are a lot of different cladding materials used on houses, such as brick, vinyl siding, or wood siding. But the exact cladding type doesn't matter when it comes to wind load path, as long as the cladding is properly attached to the wall assembly. The cladding is attached to the wall assembly, which is made up of the studs and wall sheathing. So the wind load transfers from the cladding to the wall assembly. In this graphic, I'm exaggerating the deflection of the studs, but they do deflect as they take the wind load. The wall assemblies span from floor to floor or floor to roof, so they deliver the wind force to the nearest roof or floor sheathing. In this house, that means that the lower half of the wall assembly on the first floor transfers the wind load to the first floor sheathing or to the slab on grade. The upper half of the wall assembly on the first floor and the lower half of the wall assembly on the second floor transfers the wind load to the second floor sheathing. The upper half of the wall assembly on the second floor transfers the wind load to the roof sheathing. Wind load on the roof itself is also carried by the roof sheathing. For the next step, let's take a look at the house in plan view. Once the wind load has been transferred to the nearest roof or floor sheathing, the floor sheathing and framing act together as a floor system and transfer the wind load over to the sidewalls, which contain the bracing that resists the wind load. The roof sheathing and framing act together as a roof system and do the same thing. It is important to understand that the wall receiving the wind load does not resist the wind load. All it does is send the wind load into the structure so that it can be resisted by the walls parallel to the wind load. Now let's go back to the elevation view to see what happens next. The wind load in the roof system that has now been moved over into the sidewalls is picked up by the second floor wall bracing and moved down to the second floor. At that point, it meets up with the wind load from the second floor system. The roof system wind load and the second floor system wind load combine and are picked up by the first floor wall bracing, which moves the loads down to the first floor. At the first floor, the combined wind loads meet up with the wind load from the first floor system. This combined load now includes the entire wind load of the house. At this point, the entire wind load is transferred into the foundation of the house, and the load path is complete. What is important to understand is that as you work your way down each level of the home, the wind load carried by the lateral load path increases at each level until it is maximum at the first floor. The lateral load path at the top floor of a 3-story home has far less wind load than the lateral load path at the first floor, because the load accumulates as it makes its way down to the foundation. This is the load path we are going to break down and look at in detail. We are now ready to go back through the lateral load path and look at exactly how a wind load moves through the members and connections on its way to the foundation. This is a list of the details we will be discussing for a typical 2-story house. Each one is a critical connection in the lateral load path. We will also look at the uplift loads on the roof that were mentioned earlier, since they are a major part of a wind load and also require a complete load path to the foundation. As we look at each connection, I will specify if we are looking at it for a lateral load or for an uplift load. We will start with the attachment of the studs for lateral loads. As we saw earlier when we looked at the big picture of the lateral load path, when the wind blows on a house, it blows on the cladding. The cladding transfers the wind load to the wall assembly, which is made up of the studs and wall sheathing. The wall assembly then transfers the wind load to the roof and floor systems. In order for this to happen, the studs must span from floor to floor or floor to roof. It is critical that the studs all span from level to level. In this photo of a tall wall, the studs span from the first floor all the way up to the roof, with a row of blocking at the midpoint of the wall. Engineered wood studs are ideal for this application because of their strength, straightness, and dimensional stability. One of the lateral load path failures we often see occur in this situation is when the studs do not span from floor to roof. Instead of a single long stud, we see 2 walls built of shorter studs and then stacked on top of each other. A single long stud designed to be able to resist the wind load applied to it will be rigid enough to transfer that wind load to the floor and roof. But 2 walls stacked on top of each other will have a hinged joint that will not have the rigidity needed to transfer the wind load to the floor or roof. Let's take a look at an example of what I'm talking about. In this photo, you can see the hinge failure here. The wall in this room is mostly gone, most likely because of the failure in the lateral load path at the studs. The connection between the stacked walls does not have the necessary rigidity to transfer a wind load. If there had been a second floor in this room, the floor sheathing would have been available to take the wind load and support the studs. Without a second floor, the two-story stacked wall should have been a continuous stud wall from floor to roof. Here's a close-up of that detail. Platform framing, as seen in this photo, is only appropriate where there is a floor system to support the studs. Another common location where we see this type of load path failure is at gable ends. This house experienced a tornado, but the good condition of the trees in the background indicates that the wind speed was still relatively low. Gable end failures are often observed even after events with low wind speeds, where a properly constructed gable end should have been able to withstand the wind forces. In this photo, which reflects common gable end construction, the top of the wall, indicated by the arrow, is unsupported and has the gable end wall stacked on top of it, similar to the photo of the failed wall we just saw. Again, the connection between the two walls is not rigid enough to transfer the wind load to the roof above or the floor below. This would be considered a hinged connection. Continuous studs would be an option here, with studs that span from the floor to the roof. Another option would be to brace the hinged connection to the roof sheathing. A third option for bracing gable end walls is shown here. This is a detail from APA's Building for High Wind Resistance publication. In this option, the hinged connection is braced back to 3 interior trusses using 2x4s and metal strapping. Although this is not directly tying the studs to the floor or roof sheathing, this detail has been determined by APA to provide sufficient support for the hinged joint in this situation. The next connection in the lateral load path is the attachment of the roof sheathing to the roof rafters or trusses to resist uplift loads. As we discussed earlier, wind loads don't just produce lateral loads. They also produce uplift loads. These loads produce a vertical uplift or suction on the roof of the structure. Structures must be designed to transfer these loads to the foundation as well. The IRC recognizes that the uplift forces are not consistent across the roof. Higher uplift occurs at the edges and ridges of the roof, as can be seen in figure R301.2(8) of the IRC. The loss of roof sheathing during high wind events due to incorrect spacing of fasteners is a common occurrence. In the 2018 IRC, the fastener pattern for roof panels that are 1 inch thick or less requires a tighter fastener spacing within 4 feet of roof edges and ridges, including 4 feet in from gable end trusses. This tighter fastener spacing is in recognition of the greater uplift forces in these areas. Different fastener patterns are required for panels that are thicker than 1 inch and for supports spaced at 48 inches or greater. So always check the code to determine the spacing required for your particular situation. At this home, the roof sheathing was removed from the trusses due to an uplift force. The loss of roof sheathing during a high wind event puts the house and its occupants at even greater risk. It can allow water, wind, and projectiles to enter the house and cause even more damage. It also removes the support provided to the studs that are attempting to transfer the lateral wind load into the roof system, which consists of the roof sheathing and framing, so that the wind load can be moved over to the walls and down to the foundation. Without the roof sheathing in place, the wind load has nowhere to go. Roof sheathing is a critical part of the lateral load path. In this photo, the roof sheathing staples pulled out of the roof framing member during a tornado. Staples are an acceptable fastener per the IRC, but are required to be installed at a tighter spacing than nails. IRC Table R 602.30(2) provides the required spacing for alternate attachment methods, including staples. Staples should also be oriented properly during installation, with the staple aligned parallel to the roof framing member. Another reason why the loss of roof panels is so common during high wind events is that staples are often installed with the legs perpendicular to the framing member, as seen here. Installing the staples perpendicular makes it difficult to ensure that both legs of the staple engage in the framing member. When the staple is installed parallel, it is easier to ensure that both legs engage. The next connection we're going to discuss in the lateral load path is the attachment of the roof rafters or trusses to the top plates to resist both uplift and lateral loads. As we continue to move through the lateral load path, the top plates are the next place failures commonly occur. The connection between the roof framing member and the top plate experiences a lateral load and an uplift load simultaneously when the wind blows parallel to the top plate. It is most often the uplift load that causes the failure at this location. Let's first take a look at the lateral load. This is the load that has moved from the roof system over to the edge of the roof and is now attempting to move down into the wall bracing of the wall below. Whether the connection between the roof framing and the top plate is toe-nailed or uses hardware such as hurricane ties, the majority of the roof wind load is transferred from the roof system into the top plate through this connection. The IRC requires blocking along the top plate at braced wall panels between the roof framing members in some situations. When blocking is present, it will also help to transfer the wind load from the roof to the top plate. Next, let's look at the uplift load. This load, which was initially applied to the roof sheathing, as we saw in the previous section, has now moved through the roof sheathing fasteners into the roof framing and is attempting to make its way down to the foundation. In order to do this, it must pass through the connection between the roof framing and the top plate. The IRC does allow this connection to be toe-nailed with limitations. However, toe-nailing isn't the best option for this type of load. Toe-nailed connections depend on the strength of nails in withdrawal. If you've ever pulled a nail out of a board, you know it's fairly easy. Even if the uplift load under the wind speed specified by the IRC allows for the connection to be toe-nailed, a high wind event can easily exceed this load and cause a failure at this connection. We've already discussed the importance of maintaining the integrity of the roof system during a wind event. Using simple metal connectors at this connection can make a big difference in these situations. Take a look at some of the load path failures we have observed regarding this connection. The failure of the connection in this photo is most likely the result of uplift forces. Another risk with toe-nailed connections is that toenails aligned along the grain can contribute to splitting of the framing member, which can cause the connection capacity to drop even more. An inexpensive metal connector would have likely prevented this failure. At this building in Missouri, the roof trusses could be seen on the ground after a wind event. The only attachment of these roof trusses to the top plates was toenails. The strength of this connection was insufficient in this instance. The toe-nailing in this roof rafter connection simply cleaved the framing member during a wind event, leaving the nails intact in the top plate. Our next connection is the attachment of the top plate to the wall sheathing to resist both uplift and lateral loads. First, we will talk about the uplift loads. In a typical framed house, there are two top plates at the top of the wall on which the roof framing bears. We will refer to these as the upper top plate and lower top plate. We just talked about how the roof rafters are transmitting the uplift load into the wall through a connection to the upper top plate. From the upper top plate, the uplift load will next move into the wall assembly in order to make its way down to the foundation. This is another connection in the load path where we frequently see failures during high wind events. The reason why this connection fails so often is because the wall sheathing is not attached to the upper top plate. When the wall sheathing stops at the lower top plate, the wind load must move from the upper top plate to the lower top plate before it can move into the wall sheathing and wall assembly. These two plates are typically face nailed to each other. This creates a connection that is dependent on nails in withdrawal when an uplift load is attempting to move from the upper to the lower top plate. As we have already discussed, nails in withdrawal are not reliable during high wind events. Let's look at some photos of this connection failure. On both of these houses, the wall sheathing did not extend and attach to the upper top plate. When the uplift load on the roof attempted to move from the roof framing down to the wall assembly, the upper top plate began to separate from the lower top plate. In the top photo, you can see the face nails withdrawn all along the upper top plate. Connecting the wall sheathing to the upper top plate can help eliminate this failure. These hurricane ties worked well for holding the rafters to the upper top plate. Unfortunately, the load path still failed at the connection between the upper and lower top plates, and the roof was pulled off of the house. A nail can be seen sticking out of the upper top plate where it failed in withdrawal at its connection to the lower top plate. Because the uplift load is being transferred from the roof at the roof framing location to attach to the upper top plate at all locations around the house. Wherever there is a roof framing member, there will be an uplift load. A connection between the sheathing and the upper top plate is critical to a strong load path for the uplift load around the entire perimeter of the house. After the uplift load is moved into the wall sheathing, it is carried down to the level below through the wall system, which is a combination of the studs and wall sheathing. Now let's look at the lateral load that is moving through the connection between the top plate and the wall sheathing. As we discussed earlier, the lateral load has moved from the roof system to the upper top plate. Both the upper and lower top plates act as a collector by gathering the lateral load as it comes down off the roof system and transferring that load over to the bracing locations in the walls. At the bracing locations, the top plate transfer the load into the wall sheathing through the wall sheathing fasteners. The lateral load is only transferred to the wall sheathing at wall bracing locations. Now that the top plate has transferred the lateral and uplift loads into the wall sheathing, we're going to take a quick look at how the wall sheathing and framing worked together to transfer the loads down to the level below. After the uplift load is transferred into the sheathing of the level below, the sheathing and the wall framing work together as a system to move the uplift load down to the bottom of the panel. The code does allow the uplift load to be reduced by the dead load of the structure. So this load will get smaller as it moves down past each level of the house. Once the lateral load has moved into the wall sheathing at the bracing locations, the sheathing and the wall framing again work together as a system to move the load down to the bottom of the panel. Code requirements for panel fasteners are 6 inches at the panel perimeter and 12 inches at intermediate framing. If the bracing is an engineered shear panel, the engineer may require a tighter fastener spacing to accommodate a larger wind load. Shear wall performance is greatly affected by the fastener pattern, so ensuring that the fasteners are installed at the spacing noted on the drawing is critical. We are now going to look at what happens at the second story as the lateral and uplift loads from the roof move down to this level. Now that the second floor bracing has moved the lateral load from the roof down to the second floor, the load needs to move from the second floor bracing into the first floor bracing. At this connection between the two floors, the top plates of the first story walls act as the collector. The lateral load moves from the bracing locations on the second floor through the wall sheathing fasteners into the collector. It then travels along the collector until it comes to a bracing location on the first floor. At that point, it moves through the wall sheathing fasteners into the wall bracing on the first floor. The uplift load is also moving through the wall sheathing down to the second floor. This load will also transition to the first floor sheathing through the wall sheathing fasteners. From this perspective, it appears that both loads take the same path through this connection. But if we take a closer look at the connection between the first and second floor sheathing, we will see that the lateral load moves through the fasteners in a horizontal direction. This load also only occurs at bracing locations. The uplift load moves through the fasteners in a vertical direction and occurs around the entire perimeter of the house. The movement of these loads from the second floor to the first floor is another area where we commonly see an incomplete or weak load path. The key to a strong load path with this connection is to make sure that both the upper level and lower level sheathing are attached to a common framing member, and to avoid a load path that depends on nails in withdrawal to transfer the load. In this picture, we showed the sheathing attached to a common framing member, the first story upper top plate. This home in Tennessee, which experienced an EF3 tornado with estimated wind speeds up to 165 miles per hour, was built with a load path that depended on nails in withdrawal to transfer the lateral and uplift loads from the upper story to the lower story. A closer look at the detail at the base of the second floor wall shows that the second floor wall sheathing stops at the bottom of the bottom plate, while the first floor wall sheathing stops just below that. This is a graphic of the detail that makes it easier to see. As you can see, the two pieces of sheathing do not attach to a common framing member. If we look at how the wind load moves through this connection, this means that after it moves from the upper level sheathing into the bottom plate, it must go through the nails that attach the bottom plate to the second floor before it can move into the first floor wall sheathing. The connection of the bottom plate to the second floor is face nailed, which means it depends on the strength of nails in withdrawal. As you can see by the photo, the connection was not strong enough to transfer this load. The bottom plate was pulled up the entire length of the side of the house. The rear corner of the house was stiff enough to hang on to the end piece of OSB, but the load was still great enough to rip the OSB in half the long way. The complete loss of the roof of the home likely also contributed to the failure of the walls. Without the roof system to support the top of the studs at the upper level, the load path was incomplete and the wall system was weakened because of it. We talked about how important it is that the sheathing is attached to a common framing member. In this image, the common framing member is the blocking or band or rim joist. The common framing member could also be the sill plate on the upper floor, blocking in the upper and or lower level walls, the upper top plate on the lower floor or the lower top plate. But keep in mind, as we discussed earlier, the sheathing should never be fastened to only the lower top plate at the roof level. At this location between 2 stories, attaching the sheathing to the lower top plate is okay, as long as both the upper level and lower level sheathing are attached to it. All of these options qualify as common framing and will effectively transfer the wind load between the panels on its way to the foundation. Another thing to note regarding the load path at this location, regardless of where the panel joint occurs, since the double top plate is considered the collector and is transferring the lateral load to the bracing in the level below, it is important that there are fasteners attaching the bracing panels to the double top plate. This will recreate the most direct load path for the wind load to move from the collector to the bracing below. In lieu of attaching the first and second floor sheathing to a common framing member, another option for transferring the lateral and uplift loads from the second floor to the first floor is the use of hardware. Hardware can eliminate the need for panels to attach to common framing members. Metal strapping is commonly used to accomplish this. The house pictured here has strapping all along the front at the second floor level. Metal strapping only transfers uplift loads. It does not transfer lateral loads. Lateral loads can still be transferred by attaching the sheathing to common framing members. If this is not sufficient, additional hardware can be used that is designed to transfer lateral loads. So far, we have followed our roof loads, both uplift and lateral, through to the first floor wall sheathing and bracing. At the same time that this is happening, a wind load is also moving through the second floor on its way down to the foundation. Let's take a look at what's happening there. We've already seen how the studs transfer the wind load to the roof and floor systems. The top half of the first floor studs and the bottom half of the second floor studs transfer the wind load to the second floor. At this point, the second floor sheathing and framing act together as a floor system and transfer the wind load over to the sidewalls. Similar to what we saw at the roof, the wind load will move from the floor system into the bracing in the first floor wall below. Again, the first story double top plate will act as the collector and will transfer the lateral load to the wall bracing locations on the first floor through the wall sheathing fasteners. When the panel joint occurs in different locations, as we saw previously, the load path is still generally the same. The wind load moves from the floor system into the collector and from the collector into the wall sheathing. The wall sheathing moves the wind load down to the level below. At this point, the lateral loads from the roof and the second floor have moved into the bracing at the first floor. The uplift load from the roof has also moved down to the first floor, either through the wall sheathing or through supplemental hardware. From the first floor wall sheathing, the loads will next move into the sill plate. This is another critical connection in the load path to the foundation. The first floor wall is attached to the foundation through the anchor bolts in the sill plate. Therefore, this is the path a load must take to get out of the house and into the foundation. The uplift load has been transferred down to the bottom of the first floor sheathing through the sheathing itself or through hardware. The lateral load has been transferred down to the first floor sheathing at the bracing locations. At this point, both loads are transferred into the sill plate through the fasteners at the base of the wall sheathing. APA has observed a lot of homes where the sheathing was not attached to the sill plate. This makes it impossible for the wind load to be able to move into the foundation, and a failure of the lateral system is almost guaranteed to occur at this location during a wind event. Another issue often observed with this connection is when staples are used that are oriented improperly. The staple should be parallel with the sill plate to ensure both legs of the staple are engaged in the sill plate. When the staple is installed at an angle, the chances of one of the legs not engaging is higher and the capacity of the fastener is reduced, again increasing the chances of a failure at this location. In this photo, we see that the sill plate has remained in place during a high wind event while the wall was lifted away from the plate with a displacement of over 12 inches. You can see that the staples were installed perpendicular or at an angle to the sill plate and not parallel as they should be installed. As a result, all of the staples visible in this photo only had one leg engaged in the sill plate, and there was not a sufficient connection between the sheathing and the sill plate to prevent this failure. Looking closely at these photos, you can see that there don't appear to be any fasteners at this critical connection. As a result, the wind load simply pulled the wall assembly away from the sill plate. The final connection in the lateral load path is the connection between the house and the foundation. We will look at how the uplift and lateral loads make this transition. The lateral and uplift loads move from the sill plate into the foundation through the anchor bolts. Anchor bolts are transferring the entire wind load applied to the house into the foundation. Insufficient anchorage resulting in a connection failure at this location is another common observation after high wind events. Anchor bolt spacing for the 2018 IRC is 6 foot on center maximum, with a minimum of 2 bolts per sill plate. The anchor bolts are required to be half-inch minimum and to be embedded at least 7 inches into the concrete or grouted cells of concrete masonry units. It is critical that this requirement is met. The code also specifies that a washer must be included on each anchor bolt. The washer is a critical piece of the assembly because it provides the surface area against which the sill plate bears when the wall is experiencing an uplift load. The lack of a washer or the use of a smaller washer can cause the sill plate to split or to be pulled up over the anchor bolt, as can be seen in this photo. The 2 anchor bolts on the right remained embedded in the foundation but split the sill plate, contributing to the failure of the wall. A larger plate washer can help prevent this type of failure. APA recommends 3-inch square plate washers to provide a larger bearing area and better support the sill plate during high wind events. Check your local code for requirements regarding washer size at bracing locations. In some areas of the country, powder actuated fasteners are used to attach the perimeter sill plate instead of anchor bolts. One of the more common problems we have observed with the use of powder actuated fasteners is that they are sometimes installed improperly, and as a result, they don't always penetrate the concrete sufficiently and instead just fall the surface. This is difficult to check during installation, so can go unnoticed until a failure occurs. At this house in Texas, the entire structure was removed from the foundation. You can see the relatively good performance of the houses surrounding this slab. The entire perimeter of the foundation was walked. It was observed that there were no anchor bolts holding the sill plate to the slab on grade foundation, only powder actuated fasteners. The fasteners that were installed in this instance were installed improperly and did not provide adequate embedment into the foundation. The rest of the structure may have held up well enough to transfer the lateral load down to the sill plate, but the weak connection between the sill plate and the foundation led to the failure of the house. If the wind load cannot get out of the structure and into the ground, it will take the house with it. Another error that is often observed with this connection is when the sheathing is attached to a bottom plate, but not a plate that is directly anchored to the foundation. In this photo, you can see the staples in the plate where the sheathing was attached. However, this plate is not anchored directly to the foundation. It is only face nailed to the plate below, which is anchored to the foundation with anchor bolts. This allowed the wind load to simply pull the top plate off of the bottom plate, snapping it off where it was weakened by the hole to allow for the anchor bolt. As we have seen in previous pictures, a face nailed connection has very little capacity when it is loaded in this direction. Ideally, the sheathing should have been extended down to the lower bottom plate and fastened into the side of it. Now that you understand what a load path is, how braced walls work, what can happen to a house when there is a load path failure, and exactly how a wind load moves through a home, the common details you see every day when you're out on the job site should make more sense. All of the connections discussed today are critical to ensuring that our homes can withstand the loads that are applied to them on even just a typical windy day. But during high wind events, these connections can be the difference between a home that remains standing and is able to protect the occupants and their possessions and a home that does not.
Wow, thank you, Cathy. I do want to point out that that QR code has reappeared on the corner of this slide. So another opportunity for you to use your smartphone, take out the camera function and shoot a picture of it so that you can launch the survey and give us some feedback so that we can continue to improve our webinar offerings in the future. So with that, let's get into some questions. First, does brick veneer strengthen a home's resistance to wind load?
That is actually a really good question because it certainly looks like it should. Unfortunately, it does not. So as we just saw, the wind load path goes through the wood framing of a house. And in order for that brick to be able to contribute to the lateral strength of the house, the wind load would somehow need to have a way to move into the brick. So there would have to be a load path through the brick. In typical residential construction, brick cladding is attached to the house with light gauge metal straps that span from the exterior sheathing into the brick veneer. They span across an air gap, actually. So there's actually a gap between the brick and the exterior sheathing. And those straps, they're light gauge. They do not have the strength that you would need to transfer that wind load into the brick. So because of that, there's no way for that brick cladding to be a part of the lateral load path, so it cannot contribute to the lateral strength of the house.
Yeah, common misperception. So another question, what about balloon framed walls? Does the load path look any different?
So in general, balloon framed walls are going to need to follow the same rules as platform framing. So that means they'll need to span from floor to roof, can't have any hinge connections because they need to be able to transfer that wind load from those studs to the roof and floor sheathing. Some of the details might look a little bit different between the different methods of framing, but overall the load path is generally the same.
Thank you. I see houses without sheathing on the gable ends. Does this area need to be sheathed?
Absolutely. It's a critical area that does need to be sheathed as well as the rest of the house. So when we were talking about how the wind load in the roof sheathing moves down into the wall sheathing, of course that happens on all the sides of the house. It depends on which way the wind is blowing, but if the wind is blowing parallel to the gable end, the wind load will still need to move from those double top plates into the wall sheathing. If there's no sheathing on that gable end, unless there's a gable end truss that's designed to transfer the shear force, there's not going to be any load path, so that wind has nowhere to go in order to make its way down to the foundation.
We received several questions, so I kind of compiled them into one question here. We use different details than some of the details that you showed for the load path. Are you suggesting that the details that you discussed are the only ones that we should be using to design a home?
No, we're not. Definitely not. There are so many different ways to properly design and detail a house to have a strong load path, and there are just really too many to include in a 1-hour presentation. We tried to show a few different examples of how to detail a complete load path, but definitely not suggesting that these are the only ways that you could properly detail a house.
Thanks. A lot of pictures you showed of damage were from very high wind speeds. Is it realistic to expect a house to be able to survive wind speeds that exceed what is specified by the code?
In a lot of the cases when we do look at wind events, what we see are houses that have been damaged in situations where actually the wind speeds were still within the code specified minimum. Actually, the house that's pictured on this slide is a perfect example. This was a straight line wind event that occurred in Rockwall, Texas a few years ago, and the wind speeds were determined to be no more than 110 miles per hour, and that's below the design wind speed of 115 miles per hour for the area. But you can see this house still sustained really extensive damage. So we see quite often houses that are designed with or built with weak or incomplete load paths, and they're just not able to withstand even the loads that are the wind loads that are below what's required by code.
We also got a lot of questions about that connection from the second story down to the first story. And so a question related to that says, you mentioned that if the common framing member at a sheathing joint is blocking above and then below the floor level, the sheathing should also be attached to the double top plate. What nail spacing do I need to use to attach the sheathing to the double top plate?
My thought would be it should probably be the same as the required edge fastener spacing. So if it was a prescriptively designed brace wall panel, that would be 6 inches on center. I know the code does not address that specific situation, but that would make the most sense to me. We want to make sure there are enough fasteners to move that lateral load from the sheathing into the collector and then back out again. So 6 inches on center would definitely achieve that, since that's what's required if there was a panel edge at that location. If we're talking about engineered shear walls, I think it would make sense to use the same concept and just use the same fastener spacing as is required for the perimeter fasteners.
And that's a good segue. There was several questions as well about this concept of the presentation today being about houses and IRC and wall bracing. And, you know, are these concepts also applicable to non-residential construction?
Absolutely. Yes, all of these examples, this applies to both. It's in general, that wind load path is going to be about the same.
Okay, your presentation showed the load path if wood panels are used as bracing. How is it different if a different method of bracing is used?
So we intentionally didn't go into all the different types of wall bracing or engineered shear wall methods, just because it's not really the focus of what we're talking about today. But in general, the load path is going to be the same regardless of the bracing method used. All bracing does the same thing. It moves that wind load from the top of the wall down to the base of the wall. Each bracing method or shear wall method is going to do that a little bit differently. But we do have, APA's got bracing webinars that are available on our website for free if anyone's interested in watching some of those and learning a little bit more about bracing in particular.
And then if flexible sheathing is used on the house instead of plywood or OSB, wood structural panels, does it still work the same way as a load path?
In theory, it does. APA, we have a product advisory regarding flexible sheathing products that can be found on our website, and I would recommend reviewing that.
A little bit off topic from the structural aspect, this next question says, if shingles blow off the roof, but the roof sheathing remains and gets wet, can the shingles just be reinstalled, or does the sheathing need to be replaced?
Now, that's really actually a common question we get quite a bit. Yes, sheathing is designed and can be exposed to moisture for a limited period of time, and it'll regain its strength once it dries out. So yes, I would say as long as the fasteners that attach the roof sheathing to the framing are still intact, since they were subjected to a higher wind load, that does need to be verified. But if they're still intact, it does not have to be replaced. You should be able to just re-shingle once the sheathing dries out.
And we're going to pick one more question and call it good on the Q&A. It says, I'm a plan checker and you've shown a lot of details that are not in the code. What do I do if I see an issue in a set of plans that looks like it might be a weak load path detail, like nails and withdrawal? How do I address this with the builder?
It's true, the codes don't detail out every connection. Both IRC and IBC do state the requirement for all structures to be constructed with a complete load path. There is no restriction against nails and withdrawal, but you would definitely be doing the builder a favor to point out any potentially weak connections, that would be one way for you to approach it. We also have our high wind publication that you could also use and share with a builder if that might help you as well.
Thanks again, Cathy. So before we conclude our webinar today, I just wanted to leave you with a few reminders. Be sure to download your certificate of completion for your continuing education units, whether that's AIA or ICC that you may be pursuing. And if you haven't already signed up for our APA Update newsletter, I'd like to encourage you to do so today. It's a very easy way to sign up. This will give you the notices for when we have new webinars that are coming up. It'll also give you our updated publications and standards. So to sign up, all you need to do is go to our homepage. And from the homepage on the top right, you'll want to click on Sign In, as shown in the box here. From there, you'll want to select Register. There are different newsletters that you can select. Today we're talking about the APA newsletter. And then here we have a map showing you where our Field Services Division field staff are located. Talented professionals like Cathy, who are located throughout the country and in Canada to assist the construction community. So if you are a designer, a builder, or a code official, and you have an engineered wood product question, you have a person that you can reach out to. All of our field reps' contact information is available on our website, so don't hesitate to take advantage of this free resource. And with that, I'd like to thank you for attending. Have a great day.